shit. Okay. Woohoo! Shall we do a woohoo? Okay. So, woohoo! All right. Okay. Okay. So, my doodles are topic specific, right? So, you see. So, what's a linear program? Lecture in a minute. This is what we're going to do today, really fast. You've already seen this first part. It's variables, linear inequalities on those variables, a linear objective function, and then sort of geometrically what this corresponds to is a convex region. I'll go over that again. The optimal solution is at something called a vertex of that convex region. It's the pointy part of a convex region. And then I'm going to show you a quick view of the simplex algorithm and duality. This is stuff that Professor Raghavendra did quickly, and I'll do it again quickly, and we'll get into it again, the simplex algorithm and duality, toward the end of in a few lectures. We'll go in more detail. So the applications, the main thing is it's a big, powerful tool, and so I'm going to show you how, given word problems, you can set up linear programs for those word problems. And now there's a certain so the word problems are. I'll tell you a couple of production and bandwidth problems and show you how to code it up into variables with linear constraints. Okay, and the constraints generally correspond to these resource limits. The variables, you can be clever here, so there's a little cleverness sometimes. Okay, so moreover, this linear program, I'm sort of being flip about what kinds of constraints. So there's you can have equality constraints, or you could have non-negative versus unrestricted variables, and they're standard forms. And essentially, they're all the same. You can reduce one to the other, and I'll show you how to do that. Okay? And then we're going to talk about AX equals B. You could write a linear program as, what's the input of a linear program? It's a matrix and the right-hand side, just like it is for linear systems, right? And so we'll look at that. Okay, so you want to plant carrots or peas? So it's $2 per bushel for carrots, $4. I mean, he did. I saw that Professor Raghavendra did lattes and what's the other thing? Cappuccinos. Personally, I just drink coffee. So anyway, so I don't eat a lot of carrots or peas either, but whatever. So you want to plant this, and now it takes some resources if you're a farmer. I'm sure none of you are, but okay. So take, maybe somebody is. There's not very many farmers anymore. Carrots take 3 units of water per bushel. Okay, I think a bushel is a farm thing that tells you how much. And peas take 2 units of water per bushel. And you have 100 units of water available to you through your water rights. And peas get 3 square yards per bushel of sunny land. So you have different kinds of land on your property. Some is sunny, some is shady. It's completely made up, obviously. This is what your garden has. Okay? So that's really... Okay. That's 10-year-old humor, which I value greatly, as you know. Okay. So the question is, how do we set this up? So how do we make the most money from our peas and carrots, right? This is a word problem. Can we set it up so that, how do we solve it? Okay, that's the question. Okay, so $4 for peas, just to restate the question. X1 is how much peas we make. X2, we're going to set up the variables corresponding to something of interest. The total money, now that we have these variables, we could write down how much money we make. It's 4 times X1 plus 2 times X2, and we want to maximize the money in general. That's what people seem to want to do with money. The peas take 3 units of water, carrots take 2 units of water per bushel, and you have 100 units of water. So now that you know how much peas you're making and how much carrots you're making, you know how much water you're using, right? It's 3 times X1 plus 2 times X2. Okay? And that should be no more than 100. Okay? Now, we have the sunny land that they use 3 yards per bushel for sunny land. So 3 times the X1, which is the amount of peas, should be less than the amount of sunny land you have, which is 60 yards. And the carrots get 3 yards per bushel of shady land, and you have 75 square yards of shady land. So you see you're coding up these resource constraints as these inequalities. Okay. Now, you can't make negative. This is one thing. You can't, grow negative amounts of peas and just grow more carrots, right? So you have these other kinds of constraints, right? So these are all... Now this is basically it. Okay? This is what the problem is. Okay? Now I've coded up this this word problem into just a system of inequalities and maximizing some objective function. And they're all linear, right? There's no squares here. I didn't do x1 squared or x1 times x2. Okay? So how do we solve it? What's the optimal point here, right? So, I don't know. In K through 12, they actually teach you to do linear programming. Does people remember this a little bit? Okay, good. That's good, because usually people don't remember it, but you have it, right? So one way to do it is you have the system. You can just try all possibilities, x1 and x2, right? All the possibilities. That's always a good algorithm. Try everything, okay? So it's slow. We don't really generally have time for it, but it usually works. But this one is really slow because trying every point is a problem, right? We don't have time for it, right? Because how many points are there? Well, sometimes at least you could write down how bad it is. Here, I don't even know how to write down how bad it is. Why is that? Because these are real numbers, right? How many real numbers are there? Well, there's a lot of real numbers, right? There's an infinite number of real numbers. There's an uncountably infinite number of real numbers, right? You learned all that from 70. So that's a disaster, right? Infinite, uncountably infinite, disaster. So I don't know how to do this, right? So I can't even sort of enumerate all the possibilities, right, in any sort of reasonable amount of time in terms of the number of variables or the number of constraints. Okay? So in computer science, we like to always at least have a stupid algorithm that works with the the size of the input, has something to do with the size of the input. Here we can't even necessarily do that. So getting started is a problem. And Professor Raghavendra showed you this, but I just wanted to remind you. So what I'm going to do is show you a picture here. And this is what you did in high school, some of you may remember. What does this 3x1 is less than 60 mean? It means that, you have to be less than this line, right? x1 should be less than 20. 3 times x1 is less than 60, so you divide both sides by it. So x1 is less than 20. So it says I should be on this side of this line. Okay, this inequality. That's what the first inequality says. The second inequality says x2 should be less than 25. Okay? So what we're doing is we're really, if you remember, this is just a line in this space, right? So we're drawing the line. 3x1 plus 2x2 equals 100. We're drawing that line in the plane. And then we're saying, well, the feasible points are on which side of it? Well, on this side of it, right? This is less than this line. Okay? This line is where 3x1 plus 2x2 equals 100. So anything on this side of it is less than 100. Okay? Okay, so that's the line. There's other constraints here. These constraints mean I have to be in this quadrant. Okay? So that's the feasible region. And finally, we could write down the objective function, and we're going to write it down as a direction. It says if I go if the slope is really has to do with the coefficients there, right? If I go over 1 in x1, or it's the same as going up 2 and 4 times x1. Yeah. Okay. So this is a line that corresponds to the objective. It's a normal. It says in this direction you keep getting better, right? And that's the best way to go in some sense, right? So if I moved in a direction that was orthogonal to this line, what would happen? Would I improve my objective function or make it worse? Right. It says, in general, if I'm at a point, it says if I go in this direction, I will improve my objective function. That's what this picture is supposed to indicate. Okay? If I go in the opposite direction, I make it worse. If I go orthogonal to it, nothing happens. It's the same. Okay? Okay, so this is like the feasible region, and there's this notion of convexity. Professor Raghavendra mentioned it, and I'm going to mention it again here. It says that this region has this property that any 2 points so this is the region. Now I'm just throwing out all the parts that don't, the lines that extend and everything, to just draw the convex body. Okay? So this is this convex body that I'm talking about. So that the inside of that convex body, that's where all the points in there are feasible. They satisfy my inequalities, right? They satisfy this one, they satisfy this one, they satisfy that one, and they satisfy the positivity in the upper quadrant. So that is this convex region. That is this region. So now, if you look at it, any 2 points, if you have x and x prime, if you look at all the points in between, they're also in the convex region. Okay? So you have this nice property that if you have 2 points in this convex region, all the points in between, on the line in between, are also in the convex region. Okay, that's what convexity means. Okay, for polygons. Okay, and he showed you examples where that wasn't true. If you have like the moon, if it's not full, if you draw the line between the 2 points, then you'll go outside of the moon. Okay? So algebraically, now why is this convex? I mean, I just am claiming it. Okay, so why is that true? That for the linear program, the feasible set will be a convex region. All right? I just made this wild claim. Why is that true? Okay? What does it mean to be in the convex region? It means that you satisfy every inequality. Right? Okay. So what we're saying is let's think about one inequality. And let's think about if x is in the feasible region, it satisfies this inequality. It satisfies all of them. Okay? And if x prime is in this region, it also satisfies this inequality. I'm using the word constraint. That's also what I mean by an inequality. So if x and x prime both satisfy an inequality, they're on the correct side of one of these inequalities, I claim that this point is also satisfies the inequality. What is this point? If alpha is between 0 and 1, what is this point? It's a point on the line. It's taking the average of the 2 points, some sort of average on the point. So for every alpha, all the points on the line, you can pick an alpha where x prime prime will be identified with this equation. Okay? So that says that this is just what it means to be on a line. You're the average. You're somewhere in between the 2 points. That's what this formula is saying. It says you're maybe 1/3 away from one of the points and 2/3 away from the other point. Okay. So now let's look at an equation. So whatever this value of x is, whatever you have for the value of x, it satisfies 3x is less than 60. That's this constraint. You also know that 3x prime is less than or equal to 60. That's also this constraint. Okay? So these 2 points both satisfy this constraint, the constraint that corresponds to this line. Okay? So now I want to argue that this x prime prime also satisfies this constraint. Okay, so think about it. Do you see why? Okay. So let me show you. Well, if I multiply this number, both sides of it, by a positive number, the inequality is still true. Right? If I multiply by a negative number, that would be a problem, but it's not. It's a positive number. Okay, so this inequality is still true for not just x, but if you scale x by alpha. It's also true here. You're going to multiply this inequality, both sides, by 1 minus alpha, which alpha is between 0 and 1, so this is a positive number, and so you get that this constraint is satisfied. Okay? Okay, so now I just add them. I add these two, right? I say, well, I can add these two inequalities. This is stuff we'll do in linear programming. We're going to sort of add linear quantities and scale them. That'll be part of the algorithm work here. So it's good to get some intuition about that. So if I add this side and add this side and this side, then I get this inequality. Right? This is less than this is less than this. The sum of these two is less than the sum of the right-hand sides. Okay? So now what can I do here? So this is x prime. This is x prime prime. So it says x prime prime satisfies this inequality. And that's true for every inequality. There's nothing interesting about this inequality. It's just I could have made this argument for any inequality. So if x and x prime satisfies all the inequalities, then x prime prime satisfies all the inequalities, which means it's in the feasible region. Okay? So that's the convexity here. Okay, so the isoclines look like this. Everybody on this blue line has the same value with respect to this green objective function. That's what I'm drawing there. Okay? So do you think the optimum of this thing is on this blue line for this region? What can I do? I can move over, right? Right? And then I can move over again. So this is nice because it says, well, there's something nice about this. It says I don't maybe need to think about points inside of the convex region. I could just keep moving this blue line until it leaves the convex region. Right? The problem I'm trying to deal with is there's too many points inside this convex region. There's all real numbers, or, many real numbers in there. So I'm trying to say, well, I don't need to think about really the points in the interior because I could keep moving over this thing as long as as long as that length of that line is not 0. If I move it over a little bit, there'll still be some part of it that's feasible. Okay, and that keeps working till I get here. Like at this point, if I move it over at all, what will happen? That whole blue line will be outside of the feasible region. Okay? So I'm moving this, I'm saying, well, if I move these blue line to the right like this, I'm get better and better objective values because my objective is improving there. So if I move it over until it exits, the highest objective value I ever see is like at where it exits or at one of these points. At one of these points, the sort of the pointy part of the feasible region. Right? Okay, the pointy part of the feasible region is not very mathematically precise, right? So what is the pointy part? Yeah.
An intersection between two boundaries.
Yeah. So every boundary, remember, is made up by these inequalities. We draw the line for that inequality, and we say we're on one side. Okay? which is a line in 2 dimensions, right? It's a line. So this pointy part here is the intersection of 2 lines, right? This is something you did. It's called a vertex of the region. It's the intersection of 2 lines, of 2 of the constraints, because in 2 dimensions, these are lines. Okay, so those are what I'm calling a vertex, the intersection of 2 lines that bound the region. Okay? So now it's good. Now we have actually a finite procedure for determining the optimum. We just look at all the vertices. Okay? And how do we enumerate all the vertices? What are the possibilities? Well, we defined a vertex. We said a vertex is the intersection of 2 lines. Right? So, how many possible intersections of 2 lines can there be? Well, how many lines are there? There's m constraints, m lines, and so there's at most m choose 2 of these intersections, and some of them are feasible, some of them are not, right? And then you check all of them. You check their objective value. You check that they're feasible. Okay, so you can now do it, at least in 2 dimensions. It doesn't take infinite time, or uncountably infinite time. Okay, but now let's talk about higher dimensions. If you have more variables, that also corresponds to a higher dimensional space. And now you have m constraints. Okay, so now how many vertices could there possibly be? So what do you think? Well, I'm going to give you some fake answers. How many vertices can be? So now you need to think back to linear algebra. Okay? So what you did is, in some grade, you did an intersection of 2 lines, 2 variables, 2 unknowns, 2 equations. Right? Now we're doing it in n dimensions. And these are constraints. Now, we're going to say the constraints happen with equality. That's what being on the constraint means. So how many constraints do you need to determine exactly 1 point in n dimensions? So you have a system of equations in n variables. How many equations do you need to have a unique solution? Yeah. N, right? N variable, n unknowns, you need n equations. And then you could possibly solve it. That may not always give you a solution, but it may give you a solution, right? So you need to have at least n equations. So you're going to have to, out of the m equations, out of the m constraints, you choose n of the constraints. And then you solve that system. Now you have an ax equals b. You solve that system that gives you a point, and that point will be a vertex, or could be a vertex. Okay? N constraints define a point. So there's m, choose n, things you have to possibly check for vertices. Okay? So at least it's finite. I mean, I don't know whether I need to go into this, but it's nice, right? Now you have an idea of what the geometry is, right? Each vertex is an intersection of n of the constraints in n dimensions. Okay? Yeah, but it's terrible. This is a terrible algorithm. So, but at least you got an idea of what's going on. Okay? Okay, so this is a better algorithm. Is here, this is what they used in practice for many, many years. Now they do something a bit different. So here, what you do is you start at a vertex. So here's a vertex, and you move to a better neighboring vertex. This is the simplex algorithm. This is this cartoon algorithm that I was going to show you. Okay, so let's start until you don't find a better neighboring vertex. Okay, let's look at this example. So let's start here. That's a vertex, 0, 0. It's the intersection of 2 lines. Which 2 lines is it the intersection of? It's in blue. Okay? x1 equals 0 and x2 equals 0. That holds with equality here, right? And I can solve for that. x1 equals 2, x2 equals 2. That's a very easy thing to solve for and find x1, x2. That's this 0, 0. Okay? Now, what is a neighboring vertex? So a neighboring vertex is somebody who's on one of the same lines, right? You drop one of the constraints and you move along the line. Is there a neighboring? So these are the two, the one at 20, 0 and 0, 25. Those are 2 vertices. Okay? So are they better? Do they have better objective value? Yeah, because they form, that line forms an acute angle with this green direction. So moving in that direction has some projection on the green line. So you're getting better in terms of the objective, right? Okay, so that's better. And indeed it's better. So now I moved from the point 0, 0 to 0, 25. And 0, 25 is the intersection of these two constraints. 3x2 equals 75 and x1 equals 0. Okay, and the objective value is better. So now there's another neighboring constraint. This one also has two neighboring constraints, the 0, 0 and the one up in the upper right-hand corner. And so we go there, and that's where we are now. That's what the simplex algorithm does. It just drops one of the constraints and then tries to move along the line to the next one. Okay, and so on. And here is the optimum. Now, do we think this is the optimal of this linear program, optimum value? Well, the picture seems to say it is. But let me show you algebraically. Also, Professor Raghavendra did this as well. Let me show you let me prove to you can't do any better. Not by picture, but just by looking at the algebra, the inequalities. Okay? So now for this linear program, any solution needs to satisfy all the constraints. Right? So it needs to satisfy in particular these two constraints. Okay? But okay, so if it satisfies 3 times x1 is less than or equal to 60, does it also satisfy 6 times x1 is less than or equal to 120? I just doubled both sides, so it's the same. Okay? Okay, if it has to if it didn't satisfy 6 times x1 is less than or equal to 120, it would not satisfy 3 times x1 is less than or equal to 60. Is that correct? Okay. So now what if I added these two? If I added these two, what do I get? 6 times x1 plus 2 times x2, and that should be less than or equal to 160, right? So that inequality must be true because these two inequalities are true for any feasible point. Okay? So what we're going to do is we're going to say, look, what I want to optimize is look at the objective function, 4x1 plus 2x2. I want to see how big that can get. I know that can't go to infinity just because, there's some upper bound on x2 and some upper bound on x1, so it can't go to infinity. I can easily check that x1 has to be less than 20 and x2 has to be less than 15. So the maximum this can be is 80 plus 30, which is 110, right? No, well, that's not right. I must have done it wrong because otherwise you would get 50 plus 80, which is 130. But I only got 120. Okay? So now, let's do this. Let's do this weird thing. If I do 1/3 times the first equation and 1 times the third equation, I get this. I get 1/3 times the first equation gives me x1 is less than or equal to 20. Right? So on the right-hand side, I have a 20 and a 100. So I add these equations, and I get 120 on the right-hand side. And what do I get on the left-hand side? Well, I have 3 x1s in the bottom equation, and I have an additional x1. So I have a 4x1 plus a 2 times x2. Right? And I know that if these two equations are valid, this equation must be valid. Right? Now, if this equation is valid, for every feasible point, those two equations are valid. So this equation is valid. This inequality has to be valid for every feasible point. What is this equation telling you? For every feasible point, it says 4 times x1 plus 2 times x2 is less than or equal to 120. What is 4 times x1 plus 2 times x2? It's the objective function. Yes! Right? What did I just show? I showed every feasible point can't have an objective function value larger than 120. Right? So what does that tell me? Does that tell me the one I found is optimum? Because its value is 120 and it's feasible. Okay? So no waving hands here, right? Just very simple proof that this is the best you can do. I'm not arguing about geometry. I'm not doing anything. I'm just adding these equations and saying, well, no feasible point can have value larger than 120, and here is a feasible point whose value is 120, so therefore I'm optimum. Okay? This is great, right? This is really good. This says you can check the solution. Now You don't even need to know how I came up with it. But if I illustrate a point that gets this objective value, and I illustrate a way to add up the equations to give an upper bound on the objective value, which is equal, then I've proven to you that I have the best solution. Okay? Yeah. Okay. So can we do better? Yeah, you should just answer no. I'll ask you to vote, but yes, no, yes, no. Okay, but maybe. Right? There's a solution. Okay. Okay, so actually, this is like I just did this, right? How did I know what equations to add up? How did I know what to multiply by to produce this upper bound on the objective? That is another linear program, which is the dual problem, which we'll get into later. Okay? Yeah.
Is the upper bound you get in the dual problem always achievable?
Yes. So later we'll show that there's always a way to do this. This is what Professor, I think he mentioned this. There's always a way to prove, if you have an optimal solution, there's always a way to add up the equations to get the upper bound which matches. Okay. There's some special cases, but yeah.
Can we bound how long it takes to iteratively figure out the best combination?
No, this is an algorithm, right? This is the whole algorithm.
How can we upper bound how many iterations to find the runtime if you want to do that?
For simplex.
Yeah.
Okay, yeah. So the simplex algorithm is not known to be in polynomial time. So we don't know how to bound it. That's the answer. Okay. So it happens to run fast in practice, but there's also example polytopes. He asked, how do we know what the runtime of simplex is? And we don't. That's the answer. So, yeah. Yeah, there are examples where it takes a long time, but in practice it seems to work really well. Yeah. Okay, so more vegetables. So you can add kale like sunny. Now it's going to compete with the bushel, and you see here it was a trivial condition, right? In the sense that peas only like sunny and the other one only likes shady, but kale maybe you can grow in both, so you can add more equations, right? And this is fairly natural. You should be able to set up these problems and go forward there. Okay? So for kale, you're having two variables. How much of it do you plant in the sunny land, and how much do you plant in the shady land? Whereas peas, you only plant in the sunny, and carrots, you only plant in the shady. Okay? Okay, so this is another example, right, of how you set up a problem. But you can do, like, fancy stuff. Like, you could be Amazon, right? Amazon is doing these things all the time. Okay, and this is like not Amazon. This is old school when we used to do manufacturing. I don't mean to make political statements. They just come out, and I don't mean anything by them. I am not on either side of anything as far as you're concerned. So, whatever. Okay, so the demands. So here you're making carpets. For some reason, you know the demands every month. The first month you're going to need 100 carpets. The second, or D1. And the second month, you're going to need D2 carpets, and so on, right? This is what, okay? And your factory has 30 employees, and each one can make 20 carpets a month, and they get paid $2,000 a month, okay? So just a quick calculation: how much employee cost does it cost, or wage cost does it cost per part carpet? I think it's 20 divided by 2,000? No, it's 2,000 divided by, you know what it is, right? 2,000 divided by 20, which is what? 100, okay? Just to keep you awake, right? So now there's overtime. You could have overtime, and it's 80% extra. So you pay them, what do you pay for a carpet that's made during overtime? Well, you pay $100 if it's made during regular time. Now they get an 80% bump for overtime. So it costs you $180 to make a carpet if it's on during overtime. Okay? So it costs you more. Okay? And there's also, you can't overburden you can't use them like TAs. You can't work them until, there's some limit as to what you can do. Now you can hire them and fire them. Now there's cost to hiring and firing. You have to train them when you hire them, and you have to pay the lawyers when you fire them, which costs more than hiring, right? So lawyers cost more than training. So, and now you could store the carpets too. You can make all the carpets at the beginning of the year and just fire all your employees. That's fine, right? Okay, and then you're done. But it costs you something to store it, right? Okay, so that's $8 per carpet, and at the end of the year, you have to clear the decks. Okay, this is just the constraints. Okay, so now how do we set up variables? Okay, so what are the variables here? Okay, well, the number of workers in month I. That's one variable that's relevant, right? Because that'll tell you how many carpets you can make, right? It has something to do with how many carpets you make. Okay, another variable, and at the beginning you have the notion that there's 30 employees at the beginning of the year, so we already have a constraint here. W0 equals 30, right? In the first month, before the first month, you have 30 employees. Okay, so now another variable that's of interest is how many carpets you made, okay, in a month. So another carpet is how many overtime carpets do you make, right? Because those things cost more. Okay, this is how many people did you hire and fire? It's sort of using all the words. What happens? How much does it cost to hire a person? What if you hire 5 people? Then it's 5 times 320, right? So these all figure into your cost, the hired and the fired. SI is the numbers that are stored at the end of the month because you have to pay for the storage, right? And at the end, you know that it has to be 0, right? You can't store anything at the end for whatever reason. Okay, so moreover, none of these variables really make sense if they're negative, right? You can't store negative ones. You can't do all that stuff, right? So all of these variables have to be greater than 0. So now we set up the constraints. We set up the variables. We coded up the things of interest as variables. And now we're going to write down some constraints for this. Okay, production. What does your production have to be? So it's basically your workers are working. So it's whatever each worker can make 20 carpets, right? So they make 20 carpets per month, right? The blue is up there for each constraint. It's going to turn blue. Something will turn blue. So 20 carpets per month, plus however many carpets you make total using overtime. That's how we're doing it. So O of I is sort of oddly, it's a number of carpets instead of fraction of workers or something. Okay? You can do this in different ways, but that's how we did it. So now employment. How many people do you have working for you each month? Well, you have the number of workers is the number of workers you had the previous month, plus the number you hired, minus the number you fired. Okay? What about the inventory? How much inventory do you have? Well, it's going to have to do with the production, right? Okay, and the demand. Okay? It's going to be whatever the production is minus demand plus however many you had stored. Right? Is that what I said? Yeah, however many you had stored plus the production minus the demand. Okay, now there's regulations here where I guess the regulations is you can't overwork your employees. And so this says the number of carpets that can be made is, at most at most 6 per worker. Right, that's 30% of their production value, which is 30% of 20 is 6, and that's the 6. You get 6 carpets out of each worker using overtime. It has to be less than that. You're not allowed to overuse your workers here. Okay? Just abuse your workers. Okay, so now the objective function is you want to minimize the cost. This is a feasibility problem. You're just trying to make sure you can meet your production schedule. Right? Okay, so this is the cost for the workers. Each one costs $2,000 a month. Plus, this is the total cost for hiring. Every time you hire a worker, it costs $320. That's up there. Every time you fire a worker, it costs $400. Every time you store some number of carpets, it costs you $8 per carpet. We did this calculation at the beginning. I tried to do this to keep you awake, but also because the calculation doesn't appear. It's $180 per carpet you make using overtime. Okay? So that's one way to set up linear programs. So now you throw it in some solver and you get a solution. Okay? So once you model the problem this way, you can efficiently, well, we haven't gotten there, but you can solve it. Okay, so now here's another problem. Let's see how to model this one. Okay, so you're some company and you have you're going to lay down trunks, and basically you have users and you have your awesome network, which is not that awesome. It just is A, B, C, and D. That's what you own, right? And you know that A and B will buy bandwidth for you. This pair A, B will buy bandwidth for you. For that path, they'll pay $3 per whatever unit of bandwidth you're selling. Okay? Maybe it's a grid. I don't know. So A to C pays $2 per unit. So if you can route some amount of bandwidth between A and B, if you route 5 units, you get 15 times 5, or 15 times 2. And B to C pays $4 per unit. Okay? Now, we want to make sure that, well, here, I guess, okay. You want to make sure that every pair gets at least 2 units. Okay? You can't, freeze anybody out. Okay? So what should the variables and constraints be? What do you think the variables should be? Here you have to be a little clever. Okay? Well, one variable might be is how much do you route from A to B? Right? How much bandwidth do you route from A to B? But that doesn't really encode much, right? Because you could route it in a couple of ways. You can route bandwidth from A and B through this link to A, and then through this link to B, and then through this link to little b, to little a, and little b, through this link to big B. Okay? That's one way to route it. Okay? But you could also route it to little a, to C, and then to B, and then to little b, then to big B. Okay? So you could route it in 2 ways. Right? So we should have 2 variables. One, for how much flow, how much bandwidth do we route through from A to B through this first path, A to little B to big B. Okay, and that's one variable. It just gives us a number, right? That it will be a number. And now another one is we can introduce another variable for the other path, for this path now marked in blue here, right? From big A to little c to B to big B. Okay? So that's the second way. So now that's the only 2 ways you can route bandwidth between them. Okay, so we're done with A and B. So, and now you can define all of these for, you can define corresponding variables for A to C and A prime of C, A to C, and from B to C. Okay? Now, the capacity constraint says on edge AB. So on this edge AB, whichever ones use this edge, so the primes are the indirect paths. So whoever uses this edge, it's on the direct path from A to B, it's on the indirect path from C to B, and it's on the indirect path from C to A. So that's why the primes are there. So the total amount of flow you route through this arc from little a to little b, with capacity 6 is the sum of these 3 variables. Okay? And that should be less than 6. Okay? So that's the bandwidth constraint is XA plus XB, that we said every pair has to get at least 2 units. So that says we can't disadvantage a customer too much. Because we like the guys who pay more, we still are, maybe we're a public utility. We know about them. We have to deliver some power to everybody. Okay? Okay, so now, how many edge constraints are there going to be total? Right? This is an edge constraint, this capacity constraint. It says, well, the total of flow I send along the path that use these 3 paths that use this edge is at most 6. So how many edge constraints are there? Just to make sure you're following. Well, how many edges are there? 6. So there's 6 edge constraints. Right? It says each one of these can't be overused. Each one of these edges can't be overused. That's the constraint for this edge from little a to little b, and you have to write 6 more of them. Okay? How many bandwidth constraints are there? Well, every pair needs to get 2. So how many bandwidth constraints? These are these kinds of constraints. Every pair needs to get 2. How many pairs are there? It's 3 pairs, right? So there's 3. So that's the total. So what's the objective function now? Okay. Okay. So this is AB pays $3 per unit. How many total units are sent between A and B? Well, the one sent on the direct path and one however much is sent on the direct path plus however much is sent on the indirect path. Okay, that's the total amount of bandwidth you're providing to this pair AB, and each you get $3 for that. Okay, and you get $4 for all the bandwidth between B and C, the direct path and the indirect path, and you get $2 for every unit of bandwidth between A and C. And again, the amount of bandwidth you send is the amount you send along the direct path plus the amount you sent on the indirect path. Okay? Okay, so that's the idea here. So you can sometimes have to be pretty clever, right? Because we had to understand all the paths in this network to even produce this linear program. Okay? So it's not as direct of a production. So let's look at the production thing again. So we have these constraints, xi equals 20 wi plus O0, oi. We had this other constraint, we had this other constraint, we had this other constraint, and we had this objective function, right? So this is not the same form that I said a linear program was when I was talking about peas and carrots, right? I had less than or equal to, and when I drew that region, I was very careful to say it's this side of the region, right? So it's a little different because now there's equality constraints and there's, various other things are happening, okay? And there I was trying to max with the peas and the carrots, but here I'm trying to min. So the question is, are these the same problems as the original problem I said at the beginning? Okay? So this is what I did before. I said things like there's an inequality where some linear function over here is less than something over here, and I was trying to maximize. That was my example. That was Prasad's example. So the question is, are these actually very different? Is it a totally different problem when you have different kinds of constraints? Okay? Actually, really, it's not. The answer is no. They're actually all the same. You can convert all of these to the same kind of constraint. Like, how do you convert a maximization into a minimization? What might you do? You just multiply the objective function by -1, right? You want to maximize something, a times x. You want to minimize -a times x. Okay? So there's a trivial translation from min to max. So that's not different. How about you have less than or equal to inequalities? How do you turn them into greater than or equal to equalities? Right? What happens when you multiply both sides by -1, right? Okay, so here's an example. 4 is greater than 3, right? It is, right? That's good. Okay, so now if I multiply both sides by -1, I get that -4 is less than -3, right? So that's these are if and only conditions. Okay? Okay, so how do you turn this into equality? So this is a constraint. I'm summing some vector, the sum over all these things times their coefficients. How do I turn that thing into an equality? Okay? So what I can do is I can say this. Like, say I want to say, instead of expressing this as a bunch of inequalities, can I express it as equalities? And the answer is yes, right? What I do is I add a variable s and say it equals b. Like, if this is less than b, I should be able to add something s where it equals to b. Do you see that? Where, in fact, that's always true for anything, but when s is greater than 0. Okay? So you can convert an inequality into an equality constraint where you add a variable that has to be positive. Okay? It's just telling you this is the slack, essentially. It's the difference between b the sum of AI xi. Okay, so now how do you turn this thing into an inequality? Now, so let's say I started with a bunch of equalities, but I want to convert it into a linear program with only inequalities. How might I do that? Yeah. That doesn't work. I'm sorry. Well, maybe it works, but I don't know how it works. Okay, so that's, I lied here, right? You can't turn it into an inequality. You can turn it into more than one inequality. Like if I'm bigger than you, I'm at least as big as you, and not bigger than you, or what is it? At least as big as you, and at least as small as you, then I'm the same size as you, right? Does that make sense? Okay. Oh, I guess they didn't like that. Okay, so, yeah, it just says this sum should be at most B and at least B. Right? Does that make sense? If it's at most B and at least B, it must equal to B. Right? It's sort of a silly thing. So, now here's one. Now, in our pictures before, we had all the variables be positive. Now, how do you simulate an unrestricted variable with a positive variable? With only positive variables. Right? I said before, for some reason, I wanted all my variables to be positive. And that's sort of the standard form. So how do I do that? Okay, so what I do is I introduce two variables. Both of these are positive. If both of these are positive, then what I can do is if I have a variable x, which is unrestricted, I could say, well, x is the difference of these two positive variables. Now, the difference between two positive variables, can that be either positive or negative? Yeah, this could be 4 and this could be 3, which means it's positive. This could be 3 and this could be 4, and that means it's negative. So by replacing x with these two positive variables, the difference of them in your formula, and then restating your formula, that will make all your variables be positive. All the actual variables you run the linear program will be positive. So when I write the standard form, I can use two positive numbers here. For any real number, I could write down two positive numbers that will become that. Okay. So this is so when we do the algorithms, what we're going to do is this is sort of the form we had for peas and carrots. This is the standard form. So all linear programs we're going to look at in terms of solution will maybe start out in this standard form. And we're not losing anything. We can convert other linear programs with equality constraints or maxes or mins. We can convert them all into the standard form. Okay, so we're not losing anything by writing them down in standard form. That's what I was doing when you write down your constraints, when you're translating to a linear program, you can use equalities, you can use inequalities, you can use positive variables, and we can then convert it to standard form mechanically. Okay, so it's not a big deal. Okay, so finally I want to say you can write this as a matrix, right? This set of inequalities, just like you did in high school and 54, you could write this as a matrix. So now the linear programming problem is given a matrix and a vector B and an objective function, find the best solution.